if you have a highlighter, grab your highlighter. Okay. So we talked about flattening the curve with COVID and everything. They were always referring to what we're going to really focus on a bit more today, and I gave you a bunch of graphs where you have that bell curve. Okay, normal distribution is a probability distribution, and it is symmetric about the mean. Okay, so meaning that if something is normally distributed, right, the average will be kind of in the middle, and then you'll have both halves on either side. Like if you cut it there, you'll have two exact same halves, showing that the data near the mean are more frequent. Okay. In a graph form, normal distribution will be as a graph, it'll be a bell curve. Watch this. The mean indicates the location along the x-axis, and the standard deviation indicates the scale of the curve along the x-axis. And I just added this on the side. Can you add this as well? It's basically telling you the width of the curve. Write down next to standard deviation, that bullet. It basically will tell you the width of the curve. If it's a greater standard deviation, the width will expand. If it's a small standard deviation, it will make the curve steeper and sharper. Large standard deviation will stretch the curve or flattens it. A small standard deviation will squeeze and will make it steeper. Symmetry indicates, right? Obviously, symmetry indicates that half of the values are below and half are above. That's also a thing that you need to remember about normal distribution. Here's just some examples, right? Examples of normal distribution. Many aspects, especially human characteristics. If you were to collect that information and you plot it on a graph, it will appear to be normally distributed. It will have a bell shape. So the height, if you go by height, if you collected the height of a whole country, city, and you plot it, you'll find this height that occurs most often, which is closer to our average. And then you're going to have people either shorter than that or taller than that, but it's going to be fewer people, right? As you obviously you could have to go by age and whatnot, but that's the weight is the same thing. Migration of birds, like geese some come here like super early, and like you're like, why are you here? Like, who told you to leave, right? Like, it's way too early. And some come, but there's that sweet spot. If you were to keep track of the date, there would be the sweet spot where most birds arrive. And then there's some that come super late and some that come super early, but most of them go around a certain date, right? So you have that average. Baby birds hatching in the spring, there's that sweet spot, where most of the hatchings would occur, and it's just the way it is. The time of the year those are in heat. So the deer, right, the female deer, there's a certain time, like in the peak time is in October sometime, and that's where most of the chasing will go up, right? The bucks will chase after the does, right? So there's a sweet spot there. Amount of traffic around a certain time of day. Sisler, if I go out here at 3, what do you think peak time is? I think 3:35. It's probably like the craziest. And then, so some get picked up earlier. You shouldn't be, right? Shouldn't be picked up at 3:20, but some will get picked up way later. Like when I go out sometimes, like there's still a student or two waiting, right? So same thing. No number of COVID admissions to the hospital, right? I'm sure that staff in the hospital know that there's that time of the day where it gets really busy and then it tapers off after, right? So a lot of things form a normal distribution. So not everything, but a lot of things, okay? So here's where you need to fill in a bunch of stuff. This is properties of normally distributed data, okay? Very important that you know that. And this is probably a study sheet entry. This curve right here, if you can make a smaller version of this, then I would strongly encourage you. So frequency X along here, right, could be height, it could be weight, etc. We're just going to go like that. That usually has, it could be lifetime of battery, of bulbs, you name it, right? So there could be anything along the x-axis. Frequency always goes along the y-axis, and it's how often it occurs, right? So this right here, mu, is also known as our average. So I don't know why they use two different letters, but it is the average. The average is always in the middle. So I'd like to have that kind of, that's where most information will happen around the mean, okay? So make sure you write this down. What are these? Like you have one standard deviation, two standard deviations, three standard deviation positive, and then you have negative as well. So this is what we know, okay? We know that if you go one standard deviation to the left or to the right, we know that 68%, there's a 68% chance that someone will have a height around this parameter. And just trust me, we'll do examples later on. There's a 68% chance. So if you think of symmetry, that means that here there'll be 34% here, and there'll be 34% there. Okay. So if you go, if average is your middle, 34 to either side, adding up to 68. We know that if you went two standard deviations, so if you considered where my finger is here and where my right finger is here, if you went from negative 2 standard deviations to positive 2 standard deviations, that would actually add up to 95% chance that someone would have, let's talk about height. There's a 95% chance that someone would have a height between here and there. Okay. And so that, let me just give you the correct percentages. That would be 13.5. So in this little bracket here, 13.5, and this would be 13.5 as well. So if you think about it, this is 27 plus 68, and so it adds up 95. So this whole section here, from here all the way to there, underneath the curve, I may add. Let me add another. I want that curve to really stick out. That is what we're focusing on. The curve is what we're focusing on. So we call that the area under the curve between these two would be 13.5%, 34%, 34, 13.5. And notice that you can see the symmetry in the numbers that I'm adding, okay? Can I also make a note? Make a note to this, where this curve comes down, right? Note, curve never touches x-axis. That is very important if you don't want to lose marks, okay? It never actually touches. It looks like it sometimes, but it doesn't. It gets so close, but it never really touches. So we have 68. We go out more, that's 95. And then we'll go out one more, and that's 99.7. 99.7% of heights, let's say if we consider heights, would be between this value and this value. Trust me, down the road there will be actual heights down here, okay? Not now, because for this example I have to just keep it general. And obviously if you kept going more, you would have 100%, right? But we know we only go usually 3 standard deviations to either side, And we know that that gives us 99.7% of data would fall between this height and that height. Okay. Which means, hold on, which means that the area under here, under that sliver, would be 0.15%. And same here. Just go with an arrow 0.15%. Because if you think about it, 0.15 and 0.15 add up to 0.3, which is what is still needed to get you that 100%. Okay. All right, let's fill in that box underneath. Oh, there's actually one more thing that I need to include here. It's z-scores. Okay. Z-scores tell you the number of standard deviations that you are from the mean. So when we have z-scores, we start with 0. 0 goes with the mean, and then it's just 1, 2, 3, right? Like we just put down 1, 2, 3 like that, and then going to the left, we have -1, -2, and -3. So these values, these heights that you have here, will actually have their own separate z-scores. And trust me, it'll all make more sense to you later. For now, just write it down, okay? All right, good. The percent in each section, right? The percentage in each section. What do I mean by section is like, right? Like when you see the line cutting it like this, right? The percentage in between there. Oh, I need to give you one more, sorry. This is 2.35. And this is 2.35 as well. Percent, okay? Make sure you have that. That's 2.35, 2.35. And if you were to start over here and add up all the percentages going all the way over to the other side to this value right here, that would add up to 99.7% of your data points. So remember this, 68, 95, 99.7 is going to be a very common rule that I'm going to mention throughout the rest of this unit, okay? The percentage in each section represents the likelihood, okay? It represents the likelihood or probability of data falling within the interval. Okay. A normal distribution, right, follows the 68, 95, 99.7 rule. That's also called the empirical rule. I don't really need you to remember that, but that's another fancy name for it. I just like to refer to it as the 68, 95, 99.7. Here it is again. I just want to emphasize that, right, a larger standard deviation results in a flatter / spread out curve. Let me zoom into that. Okay. A smaller standard deviation results in a steeper, more compact curve. Remember that the total area or probability under the curve is always 100%. So if you consider all of the data points, right, like all the people considered for the survey or whatever, that's 100%. So you need to have that and to take that into consideration. let's put this into practice, because this is very abstract right now. You're like, right? Like, what is all this about, right? So let's put it into practice, and you'll see, perhaps it'll make more sense after the example, okay? So just follow me for now. You might have to blindly follow me, and that's okay. I'll lead you in the right direction, I promise. Before we do that, just one more. On page 14, some set of formulas here that you will need. Also very important. I will the boxed in always means, I will highlight that after I'm writing down the formulas, but that means add it to your study sheet for sure. When you're given the mean and the standard deviation, you can use the following formulas. To calculate the z-score of a particular height or weight or anything, you use this formula. Z is equal to x minus x bar divided by standard deviation. The z-score is x minus x bar, right, over standard deviation. You should know that x bar is the mean, right? Standard deviation is just standard deviation, and x is the actual score. Actual value you're considering. Let me zoom in a bit. Okay. And then using this one, I'm just going to use this to derive something else. To calculate the x value associated with a z-score. So let's put this in brackets. Z-score is given. I can't help but to think of a German teacher. When z-score is given, right? Anyways, if you want the score, right, sorry, not x bar, just x, right? Just x, okay? Not x bar. If you want the score and the z-score is provided, you would go z, right, times standard deviation plus the average, okay? Where z is z-score, and this is standard deviation, and this is just the mean, right? So I'm just going to leave it at that. But these ones most definitely you want to have on your study sheet, guaranteed. Okay. So I'm just going to box in this whole area. Add to your study sheet. Okay. Note the z-score tells us how many standard deviations above or below the value is located. Okay. How many standard deviations the value is located. Could be above or below. How do you know above or below? Well, a negative z-score tells you that the value is below the mean, and a positive z-score tells you that it's above the mean. That's how you know. So if, let's say your test score, let's say you score 70% on a test. I calculate your z-score is -1. What does that mean? If your mark of 70% ends up having a z-score of -1, that means that you're below the average. You're below what the average test score was for the class, right? Yeah.
What would the actual, for like calculating z-scores, would the actual value be stated in whatever we're given?
Yes, everything. You would be given everything in here. That's the only way you could calculate it. Yeah. And I rather wait for the example, and then you'll know what to do. Okay. Okay. This is the example. Okay. The height of males in Canada is found to be normally distributed. That's very important. If you see that, you're like, okay, I know something about normal distribution. I know what the graph is expected to look like. I know how it's distributed, right? 68, 95, 99.7. right? It says that the mean height is 177, and this is your average, right? And the standard deviation right here is 2.5 centimeters. That's my standard deviation. Put that symbol right next to it because we're going to use symbols more than anything else. Watch what it says. I don't always want you to do it unless I tell you to, right? Okay? You don't have to graph it necessarily. It says graph a normal curve indicating the percentages within plus or minus 3 standard deviations. Include the z-scores as well. Okay? So what we're going to do is, let's go ahead and get this out of the way. 68, 95, 99.7%. We know that already. Okay. We know that this is 34 and this is 34. You're just splitting the 68 in half. Then you have 13.5 and 13.5. I'm just building out. I'm just going out. Okay. And then this sliver here is 2.35%. This is 2.35%. Should have made it a bit larger. That's all you need to fill in. You don't need to fill in the outside sliver here. You don't need that. Okay? And in this case, we will call this height, and we are in centimeters. Okay? In this particular case, we know what x is. It represents the heights. Frequency is people. People being considered for this particular survey. And the middle is my average. So you put the 177 right here. You don't need to put units because we already know this is in centimeters. So you get it? The average is in the middle. And then you need to fill in the rest. Like every single one of these will have a value associated with it. So what's the standard deviation? 2.5. See this? So you need to add 1 standard deviation to the average to come up with this value here. So we're going to go like this. We're going to go plus 2.5. Okay. Plus 2.5, that's 179.5 centimeters we're talking about. Now we need to go, right? This is 2 standard deviations, which means that, right, you're going 2.5 and 2.5, right? Or you just add 2.5 to this one. And that gives you 182. Okay? And then you're going to go out one more plus 2.5, and that is 184.5. And that's where you stop. You only go 3 standard deviations to the right, 3 standard. Why don't you go 4 standard deviations, Mr. Dirksen? Because you could go 4, you could go 5, but it's so minimal. The amount of people that would be in here is so minimal that we just leave it, right? Like we will definitely keep that in mind, but we won't add it to our graph. Now let's go the other way. To go to the left, you need to subtract the standard deviation. Whatever your standard deviation is, you subtract it from this, right? So this will be 174.5. I hope you can see that. It's a little small. I apologize. Go 1 over, take away another 2.5. I strongly tell my students to use the calculator because these numbers are often pretty weird. And if they make a small mistake, it's all off, right? So 174.5 minus 2.5, right? That's 172. And then take another 2.5 off. It's 169. 169.5. Okay. So now you have, instead of using this, which is just a guide, you actually have put in the values, right? These are the actual values associated with, right, the average, 1 standard deviation above the average, 2 standard deviation above the average, 3, and so forth. So you can tell that the standard deviation is the width of the bars. Remember that? The bigger the standard deviation, the bigger the bars should be on an actual scaled graph. Okay. So the z-scores. Every single value has a z-score, and in the middle, the average has a z-score of 0. 179.5 has a z-score of 1, positive. 182 has a z-score of 2, positive, and so forth. We only go up to 3. Let's go to the left. This value right here has a z-score of -1. This value right here, -2. This value right here, -3. Okay. So 179.5 has a z-score associated with it of 1. 182 is 2, right? So if you have a height of exactly 182 centimeters, you are 2 standard deviations above the mean, okay, above the average. So that's where that comes in, okay? Let's answer some questions now that we filled this in. Okay, so you got to follow along here. What percentage of males, right, percentage, are between 172 and 179.5 centimeters tall? And I want you to actually follow these steps, not just do it in your head, right? So 172 is right there. 179.5 gets you to here. So we're going to add up these percentages, right? Because 172 starts right here. So we're going to add this, 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 until we get to 179.5. You could also just go 68 plus the 13.5, right? Because we know that, right, this is 68. But I'm going to go step by step. So 13.5% plus 34 plus 34. And that is 68 plus 13.5. That's 81.5% of males. Watch what my answer predicted to be within 172 centimeters and 179.5 centimeters. So we don't know the exact number right now because we would need a total number, but if this is normally distributed, then this is the percentage, this is the probability that there will be males between these two heights here. Okay. What percentage of males are expected to be taller than 182 centimeters? You go up here. Where's 182? It happens to be right there. So how many would there be above? You would go 2.35% plus what's still in that sliver? You have 0.15 in that little sliver up here, right? So that gives you 2.5% of males. The probability that somebody will be taller than 182 centimeters is 2.5% of males. So I'm in that sliver. Most definitely I'm in that sliver. Let's keep going. So we're always basing everything on this graph right now, okay? So you keep that going. I'm going to keep reading the question on the other page. I made it so that it is visible as we answer, okay? Next, what percentage of males, it's asking for percentage of males, are shorter than 169.5 or taller? Watch this. You need to follow along, right? Percentage of males shorter than this or taller than that. So we need to figure that out. I'm going to go to my graph. 169.5, people that are shorter would be in here. So that's 0.15, right? Because if this is the height we're referring to, let's just put that in there. Why not? I think you're gonna need that for now. 0.15, let's do that on the other side as well, 0.15%. So 0.15% is going to be shorter, right? So let's write that down. Shorter would be 0.15%. Taller, let's go find that. 179.5. You need to be careful here. 179.5 is right here. So people that are taller would be this plus this plus this, right? So anything to the right of that line right there, all the percentages to the right are to be added up to answer this one correctly. So we're going to go 13.5 plus 2.35 plus 0.15. And these are all percentages. So follow here. If you want the percentage of males that are shorter than this or taller than that, you need to consider all of these percentages, right? Because it says or. So we're going to add everything up like this. The or comes from, right? Or in math is adding. Remember that for grade 12 applied, okay? So then just add everything up. 13, this is 2.5 here. So that'd be 16 plus this, right? So that'd be 16.15%. And you're sometimes going to say, I was so close, right? But you have to be exact in this case. Okay? So can I just stop here for 1 second? I know some of you are probably dozing off a little bit. I don't blame you. Stats is a little dry, okay? But what am I doing here? We're actually predicting. You're predicting the heights of in this case males, right, in a particular region. This is just a prediction. Why are we making this prediction? Because we've noticed when we've graphed this that it does follow a normal distribution. Okay, when they're telling you that it's normally distributed, you can apply these rules and predict based on that. Okay, I will say this. Okay, I want you to work on. It's almost quitting time here. I want you to go back a little bit and just do this one here on page 12. This is your homework. Just do this one, page 12, in the notes, right? Not in the workbook, just the notes. Plus, review histograms and frequency polygons. Review that for tomorrow, right? So basically, folks, you need to find the mean and the standard deviation as well as the range for every single player and try to answer the questions that are below it. And I will go through that tomorrow with you. It's not a whole lot of work. You just need to, right, need to make sure you do it, right? Have a good